Here on this DeBacco University video, I'm going to go over the different line spectra of her elements so you can see some comparisons and see how these essentially are the fingerprints for each individual element. All right, we can see some quick examples here representing of hydrogen, neon, and mercury and how those line spectrums for these elements do differ. But now let's dive into a little more detail for these. So first off, we just start off with what is a line spectrum, and this is basically a series of distinctive lines of color, wavelengths emitted or absorbed by an element when its electrons transition between different energy levels. Again, think of that Bohr model and that planetary model jumping to those distinctive energy levels. Unlike a continuous spectrum as we see here, which is example would be sunlight, a line spectrum contains only specific wavelengths. We see those here, there's individual little bars. Think of them like fingerprints, think of them like barcodes, for example, because they're each unique to those different elements. So how does this basically work? What's the concept behind this? Well, we have the excitation stage, which is when an atom absorbs energy, usually through heat, electricity, and it jumps up in energy level. Visually, we don't see anything associated with that portion. Then we get into the emission. This is where the excited electrons eventually fall back down to lower energy levels. A photon of energy is released as they fall, and they emit those typically as particles of light with energy equal to the difference between the two energy levels. So again, an emission occurs when the electron falls from the excited high energy level state down to that ground state. And that emission is what we're seeing as that light. And that light that we're seeing emits a certain wavelength. And a wavelength is the energy each photon corresponds to that specific wavelength, which appears as the line spectrum. So that absorption phase, we don't visually see anything with that. That's where light with sufficient energy moves to electron higher energy level. But then when it falls back down, it's emitting that wavelength of energy that we're able to see as this line spectra. So these different types of line spectrum here, we have the emission spectrum, which is bright lines on a dark background produced when atoms emit light. We have absorption spectrum. This is dark lines in a continuous background produced when atoms absorb specific wavelengths. Either way, think of them as individual little bars, like a barcode or like an individual little fingerprint. So again, those fingerprints, how do they actually look? Well, each element has a unique set of energy levels, so the lines in its spectrum are distinct. Might seem a little overwhelming here, looking at all of these elements, quote, at the same time, but it does offer a neat comparison. We're able to see that some, for example, sodium, have very limited amount, and others like silicon here have a broad spectrum. It might be hard if I showed you these individually to distinguish them, but when we start to see them in comparisons or being able to see correlating one to another, we can definitely see that there are different patterns here. And as we analyze different lights and having this as a database, we can start to correlate or match up what elements we might be seeing, for example, in distant stars. Lastly, just some common examples just to kind of zoom in on a couple. Hydrogen, helium, neon, sodium, and mercury. This allows elements in stars and distant galaxies to be identified. The chemical composition in labs can also be identified. And just looking at this more simplified version, we can definitely see how some might have some similarities, such as hydrogen and helium, but also then some distinct differences to their line spectrum, allowing us to provide an identification for something that originally might be an unknown.